integers, z, binary operator plus, that's a group. Okay. Now, is it a cyclic group? And the answer is yes, and in fact the generator is 1. So here's your... Now can you see why the generator is 1? When you're talking about the set of integers, right? And the binary operator is plus. So if you take any integer and you add 1 to it, you just get the next integer, and you can keep doing this infinitely. In fact, this is an infinite group. Right? Its order, the order of the group, is in fact infinity, because the integers never stop. Right? They go on to plus infinity or to minus infinity, and you can generate all of them just by adding 1 each time. So the generator, the element, is of this set, of this group, is 1. That's the unit, in fact. And since the binary operation is plus, you can generate any number just by plussing 1s. Plus 1, plus 1, plus 1, and so on. Okay? So this is an infinite cyclic group. Okay? Here's another example of a cyclic group. Again, be careful with notation. This is it's supposed to be a capital Z, which means the infinite set of all integers. And this little z here, it's not so obvious, but it's supposed to just to be a complex number. Okay, so little z is just x plus I, square root of minus 1, x plus I, y. Okay, so it's just any old complex number. So this little z belongs to the set of complex numbers. The symbol for complex numbers, the set of complex numbers, is usually a capital C with a sort of vertical line like this. Okay, so that means set of complex numbers. Such that, that's what the colon means. Right? So you're describing a set here. So this little z, this complex number, to the power 6 equals 1. So in other words, this z here is the 6th root of 1, which is this, right? E to the pi I over 3. Now, can you see why that element there is the generator? Because if you raise that to the 6th power, you will get e to the 2 pi I, right? E to the 2 pi I is the square of e to the pi I, that famous formula of Euler, which is just minus 1. Okay? So if you multiply these, you will get, so if this is the generator, so G2, you just put a 2 here. So if you call this G, little g, right? The little g is the generator. So G2, you put a 2 here, so G3, you put a 3 here, and so on. And you get up to G6, you get a 6 here, so 3 and 6 cancels, 3 cancels into 6, so you get e to the 2 pi I, and that's equal to 1. Right? So this is the generator of this set. Now I'll put a bar through this one. This group is not a cyclic group. Now, in an earlier lecture, we proved that it was a group. Right? So the star here, meaning so the non-zero rationals, the binary operator is multiply. And why is that not a cyclic group? How do you prove that? Right, so let's try to find a counterexample. So if Q, now assume that the size, the absolute size of one of your elements from the rationals is of this form A over B, and then you do this to it. That means take the absolute value. So if it's minus something, well, taking this, the absolute value will give you the positive value. Okay, so let's assume that this is either greater than 1 or less or equal to 1. So if you take all powers of this, you can't get a number that's less than 1, whose size is less than 1. Okay? So it's not closed for that case, because all your powers have a value greater than 1. Right? Because of this. You take any power of this, and you get an ever bigger number, the greater your power. Now, similar logic, if it's equal to 1, so any power of it will give you a size 1, and therefore all the rationals less than 1 or bigger than 1, it cannot be generated. So it's not closed when it's equal to 1. And if it's less than 1, any power of it will give you something that's less than 1, and therefore all those elements belonging to Q star greater than 1 cannot be generated. So that's out. Okay? Now, implicitly, so how do you go about proving that a group is cyclic? Right? Well, basically, you have to find at least one generator. Right? I sort of said that a little bit before, but okay. Now, conversely, on the other side here, how do you prove the converse? How do you prove that a group is not cyclic? Now, in some ways, that can be more complicated, involve more work, because you have to show there are no generators. No generators. And if the size of your group, if the order of the group is fairly large, you're proving systematically that each member of the group does not generate, by using powers of itself, does not generate all the elements of that group. That can be a rather tedious process. Okay, so often trying to prove that a group is not cyclic can be involve more work than proving that it is cyclic. Because to prove that it is cyclic, you only have to find one element that's the generator, that can generate or create all the elements of the group just by little g to some power integer. All right. I'll stop here, clean the board. That's my new approach. From now on, it's more efficient. Let me make a general statement about this whole series, this MPC series. I'm learning from bitter experience that my major constraint is the upload speed to YouTube. Now, I'm making these lectures in China. YouTube is banned in China, and so I have to use a VPN, a virtual private network, and that tends to slow things up quite a lot. And also there's another bottleneck, not just the YouTube upload speed. There's the bottleneck, that's the internet connection between China and the US. So during the day it's chock-a-block, everyone's using it, and it's better at night. But during the day it takes me about 4 to 5 hours to upload a 10-minute clip. So 10 minutes of talking takes me 4 or 5 hours during the day, Chinese day, to upload. During late at night, it's about 2.5 hours, which is better. So this reality that I'll have to live with for quite a few years until Moore's law performs its magic on YouTube, so that YouTube can increase its rate. This basic constraint will determine the nature of my lectures in the future. So I'll try to stick to about 1 hour's filming per evening, per day, because otherwise, if I do more than that, I just cannot upload it each day. So there would be an accumulation, and we're talking gigabytes. So I rapidly run out of memory on my camcorder and on my hard disks. Okay.